So, we talked about the energy band diagram in one dimension. For semiconductors, silicon was our base model, and we saw how that sp3 electrons, they split into parts, valence band and conduction band. And the diagram was like this. You have 4 n states here. This is that valence band completely filled. So, this is completely filled. Valence band, and then you have a completely empty conduction band. With a gap Eg. For silicon, you have 4 n states here, 4 n states here, and Eg is 1.12 eV for silicon. For any other semiconductors also, this structure will remain the same. The valence band will be completely filled at low temperatures, the conduction band will be completely empty, and there will be a gap which is not much larger than the room temperature value of this K into T, which is 0.026 eV for T equal to 300 K. So, room temperature, because all our work is around that temperature only. So, it's larger, surely it is larger, Eg is larger than this, but it's not 100 times or 200 times. So, this kind of materials we call semiconductors. For germanium, this will be something like 0.67 eV or so for germanium. Other semiconductors will have their own this gap. For insulators, the structure remains the same, only thing this gap is very large, say 3, 4, 5, 6 electron volts, and for conductors you do not have this structure. There the conduction band is not completely empty at the low temperature also, and so that is, so we talked about all these things. Then at these temperatures, elevated temperatures, higher temperatures, your electrons in valence band, they may receive energy from thermal interactions with the lattice and go in the conduction band. In that case, one quantum state here becomes empty, which we call hole, and one quantum state in the conduction band becomes populated, and at any given temperature you will have some electrons here and some holes here, because thermal interactions are always there at any given temperature. So, energy is taken by the electron, given by the electron. So, those kind of exchanges are always there. So, at any given temperature, some of the quantum states here will be empty and some of the quantum states here will be filled, and therefore, you will have some electrons here and some same number of holes here. Okay. So, this kind of material where you have same number of electrons and same number of holes, these electrons are here only because some valence band electrons have received that energy. So, this kind of system, which is a pure semiconductor, is known as a intrinsic semiconductor. Okay. So, intrinsic semiconductor means, yes, the semiconductor has its own band structure, and any electron which is there in the conduction band has come from the valence band. Not only electrons can come from the valence band go to conduction band, the reverse is also possible. The electrons which are already here, this electron through thermal interactions, it can give energy, it can reduce its own energy, and then it can go and fall into this empty quantum state, and in that case you will have electron hole recombination. So, you have a electron hole pair generation when a valence band electron takes up energy and goes to the conduction band, or you also have recombination when a conduction band electron reduces its energy and goes to the valence band and fills some empty quantum state there. So, this kind of recombination generation process will go on, and at any given temperature there will be an equilibrium number of electrons and holes per unit volume. So, an equilibrium density of these charge carriers, these electrons and these holes. Okay. So, you have at any given temperature there will be an equilibrium value of electron number density and that will be same as hole number density. So, this electron number density we write as Ne, and this hole number density we write it as Nh, and this is equal, sometimes people write this as Ni, okay, Ni, I for intrinsic. Okay. So, this. Now, for silicon at 300 K at room temperature, this Ne, which is same as Nh, is, let us see, is 1.5 times 10 to the power 10 per centimeter cube, whereas the number of atoms, that density, number density of atoms is 5 into 10 power 22 per centimeter cube. So, you can see the ratio in any single, this crystal, silicon crystal, per centimeter cube you have 5 into 10 to the power 22 atoms, right, and then each atom has all those 4 bonds and all those things, and then how many bonds are broken, how many valence electrons, valence band electrons have gone to conduction band, that number is this. So, this is a ratio of about 10 to the power 12. So, 1 in 10 to the power 12. Okay. 1 electron hole pair comes from 10 to the power 12 atoms. So, it is a really small fraction. Okay. 1 part in 10 to the power 12. So, with those many atoms, with those many covalent bonds, on the average 1 bond is broken and that electron has gone to the conduction band. And that is reasonable because our kT is 26 milli electron volts and the gap is 1.12 electron volts. So, as compared to this is quite large, and therefore, the probability will be small, and hence this fraction here you can see like this. But if you compare with a good conductor, let us say copper, if you take copper, this number of atoms, that density, okay, number of atoms per centimeter cube, That number is some 8.4 into 10 power 22, 8.4 or 8.47 like that, 10 to the power 22 atoms per centimeter cube. Okay, and each atom in copper, each atom contributes 1 electron to the conduction band, and therefore this is also the number density of conduction electrons. So you can see you can compare the number of electrons, number of holes. If you add them, then also total charge carrier density is 3 into 10 power 10 per centimeter cube, whereas in a good metallic system conductor, this is 8.4 into 10 power 22 atoms, and same number is that number of conduction electrons per centimeter cube. So if you compare this number and this number, you see a factor, again a factor of 10 power 12 or so. So the conductivity of these materials will be much smaller than the conductivity of these materials. But 10 power 10 is a good number. 10 power 10 in itself is a good number, and if you compare with insulators, where the gap is very large for carbon in diamond form, the gap is about 6 electron volts, and hardly any valence electron reaches there, and therefore the resistivity is extremely high. So compared with that, then this is a nice conductor. So many charge carriers are there to conduct, but if you compare with this, then this is a poor conductor. Now what decides this number? What decides that at this temperature these many conduction electrons should be there, these many holes should be there? This is the equilibrium number. What decides that? That is decided by a function which is known as a Fermi function. First, let me write this function. This is a function of energy, and it is written as 1 divided by e to the power E minus EF, and this divided by kT and plus 1. So this is known as a Fermi function. It's a very interesting function mathematics wise also. If you try to plot this, and this temperature is a fixed parameter here. So if you look for that 0 K, T equal to 0, if you take this temperature and let's say this another constant appearing here. So let's say this is here EF, this side is energy, and this side is this Fe. Okay, and if you try to plot this here, if this T is 0, so this is going to be infinity. This is in denominator in this fraction, so this is going to be infinity. But if E is less than EF, this is a negative quantity, and so it is e to the power minus infinity, which is 0, and then plus 1. So 1 divided by 1 is 1. So for all energies less than EF, this is 1, and all energy greater than EF, this quantity is positive, and T going to 0, this will become e to the power plus infinity. So this whole thing goes to infinity, and this becomes 0, and so it goes to 0. So this is a step function. This is a step function. What happens if you go to a higher temperature, some other temperature, 300 K, room temperature, some other temperature? then this function is definitely changed, but then the change is in a very small region close to this EF, say few kTs. So, if this T is not equal to 0, then how much is kT on this scale, you have to see that, and then only in this order of this energy width only the things change. And if I redraw this, it looks like something of this sort. Something of this sort. So, only in a small region, which may be few kTs, 2-3 kTs, you can see there is a change. There is almost 1 here, there is almost 0 here, and in this part there is some change. Now, in our context, what is this function? This function Fe is probability of a quantum state at energy E having an electron. You remember no quantum state can have more than one electron. So, either it has electron or it does not have electron. So, if the energy is E of that quantum state, then the probability that it does contain an electron is given by this function. Okay. So, if you have this semiconductor, you have this valence band here, you have this conduction band here, and for intrinsic semiconductors, this EF turns out to be somewhere here in the middle. From this function at E equal to EF, this is 0 at a finite temperature. So, this will be 1 and this whole thing will be 1 by 2. So, the probability falls to half at this EF. So, in this case, EF is somewhere here. There is no quantum state here. So, although the probability at E equal to EF is 1 by 2, the probability of a quantum state having the electron, having an electron is 1 by 2. But then there is no quantum state, so that question is out. But you have to measure from here. If there is a quantum state here at energy E, what is the probability that it will have an electron? So, you have to measure, you have to calculate that probability using this EF, and that EF is here. So, this is E minus EF. So, that decides the probability of this quantum states getting populated. Then how many quantum states are here at this energy or very close to this energy, and for each of those quantum states you will have this probability, and then you can integrate over all the quantum states and so on and so forth, and one can calculate how many electrons do you expect here and how many holes do you expect here. So, that decides it, and obviously larger the temperature, more will be the electrons in the conduction band, and therefore, the resistance of a semiconductor decreases as you raise the temperature, because you have more number of electron hole pair. So, that is about intrinsic semiconductors. Now, I am talking in terms of those rectangles drawn on the board, valence band and conduction band and valence band, these electrons going to conduction band, all those things. I am talking in terms of these figures. But always keep in mind that this is a representation of energies and quantum states and populations, but it is in context of a real crystal, a real silicon solid, a real silicon wafer. And remember this structure, remember this is structure. You have silicon in this fashion. You have many silicon atoms joined in this fashion. With each of these silicon you can join these 4. So keep on doing in all 3 dimensions and you get that diamond structure of silicon. So when I am saying there are electrons in this valence band, where are those electrons? In that silicon solid. So in that silicon solid, those electrons are here. These valence electrons, where are these electrons? These electrons are in these covalent bonds. So electrons participating in the bonds, they are there. Okay. If I draw a 2-dimensional picture of this, each silicon is bonded to 4 of them. So for discussion I can draw a picture like this: 1, 2, 3 and 4. So this is bonded. 2 sp3 electrons are here, 2 sp3 electrons are here, 2 sp3 electrons are here, like that. And then this is also bonded to 4 of them. So one is this and the other is this, and then this, and then this. This is also bonded, so here like this, and so on. Okay. Remember, our board is 2-dimensional and therefore I am only drawing this 2-dimensional diagram. The real crystal is having that diamond structure, that tetrahedral symmetry and all those things that I showed here. So these electrons, these are the valence band electrons. These are the valence band electrons. Whenever I draw this diagram and I say that this is valence band and there is an electron here, I am referring to one of these electrons. They are having energy which are these one of these energies, these ones. And when I say there is an electron in conduction band, where is that? That is not participating in any of these bonds. The bond is broken. When I say a valence electron has gone to conduction band, and you have an empty state here, empty quantum state here. Here one of those bonds is broken. So this electron is no more participating in this bond. You have it has gotten extra energy and therefore it has gone somewhere else, not in any of the bond. If you give some energy, bond is broken, this particular electron is now at a much larger distance and much weakly bound, and then through thermal interactions, of course, it is getting kT, on the average kT amount of energy. And then in conduction band there are so many quantum states. At these energies there are so many quantum states, and therefore it can easily jump from here to there, there to there. It can go here, it can go here, it can go here, it can go here. So whenever I am talking of a conduction electron, I am talking of an electron which is not in the bond and very weakly bound to the parent atom, and therefore it is changing the parent atom here to there, there to there, there to there, and it can go anywhere in this solid. So this connection between this diagram and this diagram, and connection between this diagram and this diagram, that should always be kept in mind. So we will raise a question and then stop the lecture. And the question is, in all kinds of electric wiring, we prefer to use copper over aluminium. In some old models, people did use aluminium coils and all those things, but then they consumed a lot of heat and energy wastage. Why? Because copper has a better conductivity, aluminium has, as compared to copper, smaller conductivity. And therefore one avoids aluminium. Aluminium wires are not supposed to be good, copper wires are always preferred. So if a factor of 2 or so down in conductivity, is something we hate. We want copper coils, copper wires, not aluminum wires, because aluminum conductivity is something like a factor of 2 less. But here in semiconductors, the conductivity is 10 to the power 12 less. And still we are giving the series of lectures, and so much of electronics is based on silicon. What is that? What is so special about semiconductors? Copper to aluminum we don't like, but copper to silicon, that gives us a wonderful lifestyle. So think over this question. In the next lecture we will discuss that.